All right, so next up is actually picking up on October 21st, 2020. Um, so so it's October 21st, 2020. We're looking at bonding session 7 and 8. Basically, today is going to run us through the rest of the slides, more or less, get us through covalent shapes, although we're talking about the fact that they have shapes. We're not going to get into the whole VSEPR geometry. That's the rules that govern it. But here we are talking about it. We're talking about covalent bonds, how they can be polar and nonpolar. We're talking about Lewis dot structures and what those have to do with anything, how we can draw those in a covalent bond. We're going to look at other things of that nature following through the slides. So I would just say go back to maybe the session bonding 4 video where it just goes through the slides, takes 7 seconds per slide. Go through those yourself. Pause before I get to the explanation of it, because likely the explanation is going to follow the end of my class day today. I'm going to try to pause it and we'll reconvene in a moment. But just understand that this is polar covalent, Lewis dot structures, and then we're going to get into alkanes and alkenes naming, although it's going to be very brief and very tiny. So look out for that. Good work. Thanks for staying tuned, and just be ready to go with those Lewis dot structure stuff. Make sure you're paying attention to all the videos, you're writing good questions, and you're uploading the things I'm asking you to upload, including quizzes and things like that. I'm about to put that up on the link, so make sure you take a look. Go Dogs. All right, so I'm not sure where I left off in the beginning. I know this is going to seem parsed out. You won't realize it, but I started making this yesterday morning after the part 2 bonding 6 video, and I planned on finishing at lunch, but I didn't have a chance at lunch. So here we are now, trying to finish. I'm going to finish this video, get you caught up on what we did yesterday, 1021, and what we did, what we're doing today, 1022. We'll probably actually get you ahead of where we're going to be yesterday and today. But anyway, bottom line was yesterday, 1021, I was coming off a doctor's appointment, and so I came back and we talked about what went on with practicing of the naming compounds. Those several worksheets I posted already. You should go find those in the post just prior to this video being posted. We won't be doing a YouTube live today. We'll be coming to you through the videos. That way they'll be a little more cleaned up and ready to go. Once again, let me get you through the slides where we left off. Oh yeah, we did some administrative things yesterday. Got our stuff situated, got our grades understood about where we got on the atomic theory exam and atomic theory projects and other things like that. Got some of my test correction policies out there. Bottom line is it's not an expectation. It's a gift. So we can't ever ask for it. It's just something that I choose to do. But I can tell you more about that later on. You obviously have to wait till you get back in person, more or less, to be able to correct what you did or did not do. So that puts us in an interesting place. We got into, we finished that up, and we touched on just barely about polar and nonpolar covalent bonds and Lewis dot structures. Did a little bit of bare knuckle practice. Talked about diatomic molecules. That means that any element, if I say to write the formula for any element that is HON, or all the halogens, Cl, I, F, Br, At, or as I use the acronym, the acrostic is HON Cliff Bar, no, mnemonic device. HON Cliff Bar, HON Cliff Brat, really, because astatine, At, is also a diatom, HON Cliff Brat. And that just means anytime I ask for the chemical formula for any of those, H, O, oxygen, N, nitrogen, chlorine, Cl, I, iodine, F, fluorine, B, Br is bromine, astatine is At. Anytime I ask for those chemical formulas, they're written as a diatomic molecule, meaning it's Br2. Or if I ask for nitrogen, it's N2. If I ask for oxygen, it's O2. If I ask for hydrogen, we write it as H2, right? So I'm going to go ahead and show you that real quick. So it's like H, O, N, C, L, I, F, B, R, A, T. It's H2, O2, N2, Cl2, I2, 2, Br2, At2. So you should be able to see those right there. Any of those Hahn-Cliff bars, when I ask for their formulas, those are written as a diatomic molecule. Now, there are a couple ones. Now, I want to contrast that because you might be like, okay, duh, that's no big deal. But if I ask for you to write the chemical formula for phosphorus, just plain old phosphorus, you had some phosphorus, it would just be this, P. If I ask for sulfur, it'd just be S. Sodium, it'd just be Na. Okay? It's these other ones, if I ask for hydrogen, it's H2, oxygen O2, and you can see the rest. They must be written as a diatom because they just will not pair by themselves. They will find another of their own atom, and they'll pair. Bottom line is, okay, that's a reminder to that, is that, remember, covalent compounds are between a metal and a nonmetal. Let me get my pen out here. Between a metal and a nonmetal, a covalent is a nonmetal. They do not typically conduct electricity, but they can technically, there are some examples that can actually conduct electricity when they're dissolved in water. So water itself is a covalent compound, but it seems to conduct electricity, and the reason is because it has a polarity to it. So water has an area of negativity and a general area of positivity compared to nonpolar, where they're pretty much symmetrical and balanced, and so they lack that positivity. They lack that difference in sharing. So bottom line here is that we see that the electrons are shared unequally in polar covalent compounds. These are compounds that form such that the electrons are kind of centered and hover around one atom over the other, and that creates a general negative area so that the other area becomes a little bit more positive just by default. The way we draw this is called a dipole. You have an area of positivity here, and over here would be the area of negativity. Looks like a little dagger is what it looks like, what it's actually called, and it points in the area of negativity. Area of negativity is because electrons, which are shared anyway because it's covalent, valence electrons, they're shared unequally, meaning they're spending time around both or all the atoms, all the nuclei, but they're spending more time around certain atoms than others. Like in this case, this would be like nitrogen, or this would be like oxygen, and the two reds would be like water, or excuse me, this silver one would be like oxygen atom, and these two reds would be like hydrogen atom. So electrons tend to spend more time. That causes the bond to actually flex a little bit. It gives it a positive end over here, a negative end over here. That makes it polar. It also makes it dissolvable in water. So that's just an interesting point worth noting. Nonpolar covalent bonds, they're symmetrical. They share electrons equally. And there's no stronger pull from one atom over another on those electrons, so they just share equally. They normally split symmetrically. They're geometric shapes. These compounds form geometric shapes, and there's a whole database of these compounds having formed geometric shapes that's been expanded into life molecules, biomolecules, macromolecules, even larger. The bottom line is to note here is that they form these geometric shapes. There are rules that govern those geometric shapes that can be formed, and names for them, and they're predictable, and all this other stuff that goes along with it. There's a whole rule system called VS-EPR. We don't need to know that, the rules of that. It's a college chemistry situation, but we do need to understand that they exist. There are rules that govern and help us predict the geometric shapes like you see right here. This actually is a CH4 molecule where the black atom is a carbon and the white ones that come off are hydrogens, and they come off and they split and they separate equidistant from the other ones. Almost looks like a little jack toy. You know, the game Jacks. Google it if you don't know what it is. Anyway, not Apple Jacks. Anyway, this is the 3D geometric shape of the compound. For example, CH4, the VS-EPR are rules that govern the predicting of those shapes. And then we have a mechanism to draw them, called those dot structures, that allow us to predict even more clearly. So that's really where we're going to dive into, is that's forming the construct there. I asked the question, why do elements bond at all with other elements? The reason why elements bond with other elements is to get to the number 8. It's all about that octet rule. It's all about achieving that magic number 8 of their valence electrons. Speaking of, what determines what will bond with other elements? Turns out what will bond with other elements are the valence electrons. So the valence electrons are what allow that to occur. That's the whole point of it. It's all about those valence electrons are the bondability component, if you will. All right, so remember valence electrons, we can tell these by looking at the group number. Group number, the A group number, like 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, those tell you the number of valence electrons the atoms have that are most readily available for bonding. When we're drawing Lewis dot structures, just as a reminder, we've done this a little bit, you've seen this before in the past. What we first do is write the symbol for the element that we're doing. As we get more complex, we'll actually write the elements because there are multiple elements in a compound for drawing Lewis dot structures. So in this case, starting off, just reminding of the rules, write the symbol, look at what group it's in, find out how many valence electrons it has, put those dots around it. This says to start at the right and count counterclockwise. You can also start at the top and count counterclockwise. You can actually theoretically start on any side. It's just typically the sides that most books and scientists start on are on top or on the right. And as long as you don't have more than 2 dots per side, meaning a total of, no more than a total of 8 around it, it doesn't necessarily matter. Bottom line is you just need to have the number of valence electrons around it as dots. Once again, no more than 2 per side. Typically start at the right or top, but it doesn't really matter just as long as no more than 2 per side. And then notice lone electron, lone electron, lone electron, and this is called a lone pair. Cool. So I ask you to try these on your paper and also ask you on the document that I'll upload for this with this video. The very first interactive notes is what it's called. The slides are in Google Classroom in bonding, right through the slides that we're in. We're in the bonding folder, Night Chemistry class docs. It's in our resources of classwork. It's in our, I've posted it 7 times a Sunday. It's in your Google Drive. It should be under shared with me, the folder, Night Chemistry class docs. Find bonding, rewind this, go back and listen to what I'm saying here. Anyway, that first asks you to determine the number of valence electrons. Then I give you about 30 seconds to draw the Lewis dot structures for each of these. So pause now, make sure you got that document open, and try to draw the Lewis dot structure for each of these. Because here comes the key. Pause now if you haven't tried it already, and then fill this into your notes. 3, 2, 1. These are the Lewis dot structures for each of these. We have hydrogen has 1 electron, so 1 dot. Carbon, 4 electrons, 4 dots. Oxygen, 6 electrons, 6 dots. Nitrogen, 5 electrons, 5 dots. Chlorine, 7 electrons, 7 dots. That's Lewis dot structure for the elements, and it's pretty simple. The next skill we need to be able to do in drawing Lewis dot structures for compounds is to add up all the valence electrons for all the atoms involved. So in the compound H2, the diatomic molecule for H2, each H brings 1. There are 2 H's. So 1 valence electron because it's H, 2 atoms because the subscript is 2. 1 times 2 is 2 valence electrons in the compound. H2O, it has H2 again. So, of course, that means there's 2 H's, so you subscript 2, 2 atoms. Each H has 1 valence electron. That yields a total of 2 valence electrons because of the H's. But it also has an O in it, which has 6 valence electrons. The O is only one of them, so 6 valence electrons because of it. Grand total, 8 total valence electrons for that. If you didn't follow that, rewind. It's easier than you think. You're probably overthinking it if you don't follow. You should follow. Let's try it again though. CH4. Carbon brings 4 valence electrons. H brings 1, but there are 4 of them. So a total of 4 from the hydrogens, 4 from the carbons, total of 8 for the entire compound. You might notice a theme here. NH3. Pause. Try it on your own. 3, 2, 1. Here it comes. N has 5 valence electrons. H has 1, but there are 3 of them. So 3 total valence electrons from the H's. 5 from the N's, grand total 8. There's your theme. Theme is the octet rule. Every atom wants to achieve that 8 electrons in the outer shell. There's only 2 exceptions, and it's technically against its own rule called the duet rule. Hydrogen and helium are the only ones who really are good at 2. All other ones want to get to 8. That's why they're bonding. So we use the need for elements to get to 8 when we're drawing those dot structures to guide us in drawing it by making sure every atom has 8, making every hydrogen have 2, will satisfy everything. Now, once again, these Lewis dot structures help you to predict a 3D geometry. There are rules that govern it. We basically just need to know that the rules exist. So here are the steps in drawing a Lewis dot structure, and we'll remind them later on. We've already done them a little bit. Got to be able to know the valence electrons amount for everyone, every element involved. You need to be able to add them up. H's are 1 each. There are 2 of them. 6 per oxygen. There's a 1 of it. Adds up to 8. Then you find the central atom. Typically, it's just you just draw the one with the fewest. Like oxygen, there's only 1 of them in this compound, so we would draw it first. You draw it, or you draw the one that's closest to. Usually, it's the one that's the fewest of. You draw the one with the most need. Anyway, we'll see as we practice. It comes naturally as to deciding which one's the central atom. In this case, H2O. The O is in the middle. The H's go out to the side. This is just how you draw this dot structure. You start by drawing symbols. So we draw the symbol. We've already added up the valence electrons. That's going to be our double check. Then you draw single bonds between the atoms, like so. And remember, single bonds represent 2 electrons. They equal 2 electrons. They have a value of 2 electrons. And they count as being shared between whatever they're between. So this bond represents 2 electrons shared between this hydrogen and this oxygen. And this bond counts as 2 electrons that is shared between this hydrogen and this oxygen. So yes, the oxygen is double dipping. Yes, those bonds count for both atoms. So then we need to fill in all the dots in order to achieve 8. So that's where the 8 rule comes in again. Still have one more step after this, so don't get ahead of me. So we see that hydrogen has 2 electrons flowing around it. How? We don't have any dots yet. Remember, the bond counts as 2 that are shared between these 2 atoms. So this line counts as 2 electrons for both hydrogen, and it also counts as 2 for the oxygen. So it's satisfied because it meets the hydrogen duet rule. Remember, hydrogen just has to have 2. This hydrogen likewise has a single bond, so 2 electrons are shared with it. It's satisfied as well. The oxygen, though, only has 4. Where's it getting those 4 from? Well, this single bond is shared with it, so that's 2 that counts for it, and 2 that counts for it from this other single bond. 2 and 2 make 4. So it's not good because it needs to get to 8. Good job. 8 electrons is what it needs to get to, so it's going to have to, this is where we fill in extra dots. We draw in dots to make it achieve 8. So on the sides that don't have bonds, I can fill in dots. Made 4 more dots, and that gives it 8. And so now it's happy. And that is the Lewis dot structure for water. Wait, we have one more step. The last step is count the dots and make sure they add up to the total. Remember the total we found out in step 1? The total we found out was 2 hydrogens and an oxygen makes 6. 6 and 2 makes 8 total. So we need to make sure we have no more than 8 in our final picture. Turns out 1, 2 in the bond, 3, 4, 5, 6, 7, 8 in the other bond, and the dots adds up to a total of 8. 4 shared, 4 pairs, how we can say it, equals the total. That was our total that we first counted on. Check it off. So the steps we can simplify are VCSOR. Oops, I'm over the top of it for you. VCSOR, that's count the valence, draw the central, single bonds, give it the octet dots, recount. Be good to go ahead and count those electrons from the start. So in this case, CH4, CS4, H4 has 4, total of valence 8 valence electrons. So I'll just need to keep that 8 circled up there good. Okay. Then we have, draw the central atom, carbon, and then the other hydrogens around it. Spread them out. I mean, do it make sense in a flat piece of paper, geometry sense. Then draw your single bonds. That's step 3. For our central atom, we did our valence. We did our single bonds. Now we need to count octet dots. This hydrogen has 2. Hydrogen has 2. Hydrogen has 2. Hydrogen has 2 because of the single bonds. Then, so each of the hydrogens are good. This single bond is shared with carbon. That's 2. 2 on carbon, 2 on carbon, 2 on carbon. That's 8 total around carbon. So carbon doesn't need any dots. It's got 8. It's satisfied. check the octet dot rule. Now let's recount the total number of electrons. 2, 4, 6, 8, and the valence in the bonds. That matches 8 valence from the count, the original count, so the recount is good. Check. NH3, I may have been moving too fast. That's okay. Go rewatch it if you want to. I would just say go ahead and watch this next one, the next couple ones, and I bet you'll be able to track with it a little bit better. So just relax. We're gonna practice. NH3 has 5 electrons because of N and 3 because of the hydrogens, giving you a total of 8. That's good for the recount later on. So we draw our central atom and the hydrogens. We put in single bonds. We check for 8. 2 for hydrogen check, 2 for hydrogen check, 2 for hydrogen check. Check, check, check. For nitrogen, 2 for nitrogen, 2 for nitrogen, 2 for nitrogen. That's 6. Oh no, it needs 8. So I need to draw in 2 more dots. Or here they are, they're up here. Now recount, make sure we have 8 that we first checked in the total thing. 2, 4, 6, 7, 8 total electrons. That checks out. See it again. CCl4 a little bit more complicated when you're not using hydrogen, because you're not going to achieve that 8 number. You might get a number that's divisible by 8 or really close by. Either way, you'll see what I'm talking about. So first thing is count. 4 carbon brings 4. Each chlorine brings 7. There are 4 of them going to be involved in this compound because of the subscript 4. That means the chlorines are responsible for 28 electrons and a total of 32 for the entire compound. So valence electrons are counted. Draw the central atom. There's the fewest number of carbons, so we'll put it in the middle. And the other compounds. We draw our single bonds between them. Then we count dots. See around the chlorine, there's 2. Ooh, it needs 8. So I need 6 more. 2, 4, 6, 8, 2, 4. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And then carbon already has 2, 4, 6, 8 from the single bonds. We need to fill in only the ones for chlorine. I don't know what happened to this L right here, but it's supposed to be there. Anyway, fill them in and make them have octet dots. Check. Now they all have 8. They're all satisfied by 8, but we got to recount. So we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. There are 4 of those sets. 4 times 8 is 32. That checks out. So can you draw the Lewis-Stock structure for fluorine? Try it. If you get stuck, use the steps. If not, just try straight away. How many valence electrons do they have in total? Pause and try, and then draw the whole thing. There's space for this on the interactive worksheet. Keys coming in 3, 2, 1. Each F has 7 valence electrons times 2 makes a total of 14. So F2 is going to be F and F. So I've counted. I've drawn, I drew my central atom. I draw a single bond. I make my dots around to get the number 8. And I recount. 2, 4, 6, 8, 10, 12, 14 dots. That matches. That's satisfied. Check yours. Make sure it looks like that. There's a little worksheet where you write the predicted structure. This is just kind of you try it. It could be the same. You could end up getting the correct structure. But this just gives you space in case you need to make corrections. On the worksheet, try it, finish it. Pause now. Go work on that worksheet. That's what I would be doing in class. That's what we're going to be doing today, 1022 in class. And then predicted structure is kind of like homework and first draft. Corrected structure, we'll check. I'm actually going to do this as classwork, but I'll check the corrected structure coming soon. So pause now, do it, try it, all those ones, all those practice ones on the worksheet. And then I will pause it. Go do it, because coming soon is the key. As promised, key's coming for fluorine and NF3, or nitrogen trifluoride, and C4H10, not tetracarbon dehydrogen. It's another name. We'll get into those today as well. Nevertheless, here they come. Pause it if you haven't done it yet. 3, 2, 1. Here's the key to those practice problems. So if yours are different in the predicted column, correct them and to look like this, or draw the corrected structure if yours does not look like this. One big thing is the C4H10 is that there's fewer C's, so call it the central atom, and then put the H's, kind of spread them out around it. That's kind of just, you go with what makes sense. And H's don't make 2 bonds because they only need 2 electrons, so you wouldn't put an H to an H. If I went like this and didn't have this one here, that wouldn't work because this H already gets 2 electrons. It satisfies its rule by putting the 2 there. So on some things you can make, when there's many central atoms, you can make a chain. That's one kind of thing that's gleaned from this. Anyway, here comes some more. Oxygen, O2, 2 oxygens, 2 times 6 is 12 oxygens. That's our valence. Central, there are 2 of them, draw them, put a bond between them, count your octet dots, and then check. 2, 4, 6, 8, around that one, 2, 4, 6, 8, around that one. Octet satisfied, but wait, let's recount. If we recount the total, it needs to be 12. So 2, 4, 6, 8, 10, 12, 14. Wait, I have 14. That's too many. What can I use that counts as dots? How can I reduce the number of dots, of electrons? I need to make electrons total go down for the whole compound, but still be 8 for each atom. What counts as 2 electrons for each atom, but only 2 for the total? What counts and acts like 4 electrons, but only counts as 2 for the total? Well, this bond counts as 2 for each electron, and only 2 towards the total. So I wonder if I could draw another bond and erase 2 dots from either side. Do they still check out on the octet dot rule? Does this oxygen have 2, 4, 6 from this line, 8 from this line? So 2 from this line, 2 from this line makes a total of 2 each. So 2, 4, 6, 8 around that oxygen. 2, 4, 6, 8 around this oxygen. So the octet dots rule is checked. And now let me recount and see if that equals 12. 2, 4, 6, 8, 10, 12. Now we have 12. So drawing that extra bond reduced my total electrons, but still maintain my octet rule satisfaction. Neat. That's the rule. You need to reduce your total, draw another line, erase dots from each, because the line counts like 2 for each in octet. But in the total, it counts as a reduction of 2. It undoes 2. Okay, watch CO2. 16 total. C in the middle. Draw my singles. Draw my dots. Check, check, check. 2, 4, 6, 8 for oxygen. Same. Carbon, good. 2, 4, 6, 8 for carbon, we're good. But wait, 20 electrons. That's too many. We're supposed to only have 16. We're off by 4 now. If you're following, you probably would see that we're going to need some more bonds. So let's draw another bond for each of them. This single bond counts as here and here, so I need to erase the dots. This bond counts as here and here, so I need to erase the dots and erase the dots from carbon. And now do I still have the 8? 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for oxygen. The 8 rule is satisfied. Now the recount, 2, 4, 6, 8, 10, 12, 14, 16. That's our total. And it's satisfied. You see how this works. The extra bond satisfies the total recount and also satisfies the octet dots as needed. Look at N2. Pause and try to do it on your own if you haven't. Yields 14 electrons. We need 10. So for every 2 electrons we're off by, we need an extra bond. Even a third bond. Interesting. Go back and watch if you need to. That one again. Triple bond is the highest number of bonds any atom can have. 4 total bonds are the most any atom can have at all bonded to it. But you can only have 4 or 3 bonds with another atom. Triple is the highest that can go. Pretty cool. So remember, a bond line counts as 2 electrons. Their count is shared between the 2 atoms. And we can use those to reduce our total number of electrons as long as we erase the dots around the outside. We need to satisfy the 8 rule and the total rule because it has to be satisfied the recount because that's just the number of valence electrons that are present. Trying to satisfy what is reality, so we can't break a rule that is reality going on. This yields us to some 3D structures. And I'm really just going to smoothly go through this. I'll go back to the day 3 or 4 video that shows you the slides just playing. I would go back through those and pause through if you need to. Go to the slides themselves, go at your own pace. This is really just to understand. Let's just see that there is geometry that we can predict. Polarity is where we go through next. It kind of mentions the things I mentioned already. Here's some examples. This I'll also attach with the video. I want you to try these slides on your own. What do you notice? Try to fill out that worksheet. Go through these slides. I'll probably spend more time as needed later. Once again, fill through the slides. This symbol is just a lowercase delta symbol in Greek. It's like the letter D, but it's a Greek symbol. It means partial. So there's a partial negative charge, partial positive charge. That's called a dipole or a Lewis pole dipole. Or a hydrogen bond sometimes. Polar bonds are asymmetrical. Polar compounds are asymmetrical. We can predict it based on its geometry and its Lewis dot structure. Go through these. This I breeze through. I'll probably come back to at a later time. It's actually more important is hydrocarbons. So these are special named compounds, and they are also covalent. We go over their naming, but you'll see their naming is actually pretty easy and formulaic. It's easiest because I show you this little worksheet you can fill in. I'll attach this as well. You can fill in that worksheet and notice that it's this table of how they're named, and it's very straightforward. It's mathematical, but you'll understand. These are called alkanes, alkenes, alkynes, and aromatics. We mostly focus on alkanes, alkenes, and alkynes. Saturated means it only has single bonds. Unsaturated means it has any number of double or triple bonds. Unsaturated just means double bond or extra bond. Anyway, saturated means no extra bonds, are all singles. So these are string-like compounds that form chains of carbons with hydrogens that branch off, and we can actually stop drawing the hydrogens in our Lewis dot structures for these as we get better at it. For now, we have to, but understand that these are alkanes, hydrocarbons. They have only hydrogen and carbons in them. Lipids and fatty acids are like this. I'm going to breeze through the slides because, once again, I have a better way of teaching this. You should go and read these slides. Please do it. Check it out. I've got a table, though, to show you how they're named. Alkenes, alkynes. Pause on these slides. They're still important. They're worth looking at it. But just know I have a better way. I'm about to show it to you. All right, so this is the table I normally show whenever I teach this. And for alkanes, alkenes, and alkynes, starts off with the number of carbons, and they're just slightly different prefixes used for some of these. And then I basically ask you to deduce and see if you can fill in the rest of this. I guide you on a couple of them, but I see if you can fill in the rest of these parts as you go. So I want you to try that. And then I want you to see the key coming up soon. So pause, see if you can fill out a couple of these. I'm going to tell you this one is called butane. And meth, bute, prop are the biggest ones for naming these compounds that are most difficult, most unknown. I'm sorry, it goes meth, eth, pro, bute, and then it's pentane, pen as the prefix, hex, hept, oct, non, dec, all the same prefixes as for earlier covalent compounds. They're just used on this worksheet here. But meth, eth, pro, bute are the only ones that are different for prefixes, and then try to fill in the rest. Here comes the key. So pause if you haven't finished it already. I want you to pause now and study these a little bit, understand, fill in yours as needed to match this. And good luck. Ask questions. Let me know about the different ways these are named, the formulas. There's a mathematical way to it. It's back in the slides. Please go look at those. Please come up with questions. That's the end of the teaching for this unit. This is bonding, day 7 or 8, I guess. Please, please, please get it done. Get it taken care of. Get those worksheets finished, the ones online that were due yesterday. All the different naming practices of a giant one coming up soon too. Get it done. Get it practiced. Send me your questions. Go Dogs.